Okay, so welcome everybody to this first international workshop on organizing and optimizing proof logging systems. Whoops. So the purpose of this first talk is to somehow give an overview, make sure we're on the same page for the talk that will follow. And as I'm revising these slides, this list of people who've been involved with me on joint work on pseudo-Boolean proof logging just keeps growing. I should say there are also more people who actually work on pseudo-Boolean proof logging, but I don't think we've had published joint papers so far. So this list is even expected to grow. So yeah, so why are we here? Well, one reason we're here is that the clicker can be convinced to cooperate today. Not cooperating, it's great. Okay. Right. Oh, it's working better. So one reason I think why we're having this workshop is the amazing progress since roughly around the turn of the millennium in combinatorial optimization solvers, which is very disturbing for me as a theoretician. These problems are supposed to be NP hard, exponentially hard to solve, and yet you have not only SAT solvers, but constraint programming solvers, mixed interlinear programming solvers, even satisfiability modulo theory solvers that solve undecidable problems very, very efficiently in practice. But one other reason, I think there are maybe three reasons why we're having this workshop. So that is the first reason, the amazing developments of modern combinatorial solving. Second reason is, well, these solvers sometimes get it wrong. And it's important to stress, I think, how badly they can get things wrong. To the extent that they even claim solutions that are not even solutions, that are not even consistent with the constraints. And of course, it gets even harder. I mean, that should be easy to fix, but something that is not so easy to fix, how do you prove infeasibility? How do you give a convincing argument that there is no solution or that the solution is optimal? And here, I think one other important observation is to counter the argument from some people that say, well, we don't care about optimality anyway, because if we're in 5% of best possible, then that's good enough for us. I mean, for instance, the airline company that some of you took to come here, they're happy to solve their MIP problems within, 5 or 10% or whatever, as long as they're making money. But there are settings where we really, really care about getting the optimal solution, or maybe your combinatorial solver is running as a subroutine inside some larger program, and they're even off by one errors can lead to completely uncontrollable errors. So I would argue we really, really care about correctness, not always, but sufficiently often that we don't want our solvers to be buggy. So what do we do about this? Well, we test our software. And it's important to stress that this is important, it's useful, it's powerful, especially modern techniques like fuzzing and delta debugging can be amazingly efficient, but somehow testing inherently suffers from the limitation that you can never prove the absence of bugs. Like fundamentally, the only thing that testing can do is to identify the presence of bugs. Another very attractive approach is to use formal verifications, to design correct by construction software together with a proof that the algorithm is correct and has been implemented correctly. And in some sense, you could argue that this would be somehow the gold standard, the final goal. The problem is that modern combinatorial solvers are so complicated that just current state-of-the-art informal verification just has no possibility to scale to the level of complexity. So the third reason why we're here is that this workshop is advocating a third alternative, namely proof logging, or that your algorithms should be certifying, which means that they don't only output an answer to your problem, but they provide also a proof that this answer is correct. So just to make absolutely sure we're on the same page, what does this mean? Well, so you have your solver in the standard setting, it would get an input and it would provide some kind of answer, maybe an optimal solution or a reporting feasibility or whatever. Now it should also output a machine readable proof. And then we have a special purpose proof checker that will take the input, the answer to the problem and the proof, and it will check whether it looks legitimate. And if so, it will issue a verdict that yes, this is okay. The answer is okay because the proof establishes this or not. Okay. So this is what we mean by proof logging. And now it's important to immediately take a couple of step backs and think about what would we want from this. Well, on the one hand, the solver is a really complicated beast. And we're expecting the proof to be fairly complicated, right? Because it's going to express all of this immensely complicated, sophisticated reasoning going on inside the algorithm. So any proof system, then it stands to reason that mirrors what the solver is doing had to be an extremely powerful proof system then. But then on the other hand, the whole point with proof logging, I mean, the whole point why we're running the checker rather than just running the solver twice and checking that we get the same answer twice, which is actually one solution I got proposed from a senior colleague, why, as an alternative to proof checking, but let's not go there. I hope that we in this room understand why this might not be a good idea. The reason why it shouldn't be a good idea is that the checker should be super simple. I mean, the dream scenario would be it's something that a good bachelor student can code up in a day. Okay, so like you can just stare at the checker code and you can really believe that, okay, if you're like this piece of code, I'm sure I got it right. And that sort of tells you, well, then if so, the proof system has to be that simple. Spoiler alert is that we're not quite going to reach that level of simplicity, but that's sort of our clear target. And there's a conflict here on the one hand, on the solver side, we want our proof to be very, very powerful because we want it to capture powerful algorithms. On the checker side, we want it to be trivial because we want to be able to trust the result. And there's a clear tension in between the two. So maybe this is a little bit too good to be true. And of course, the message of this introductory talk and the message of the whole workshop is that no, we believe, in fact, that it is not too good to be true. We think this can be done, and sort of an amazing thing, it seems that it can even be done for lots and lots of different algorithmic paradigms with a single unified method, okay? Which, spoiler alert, is going to be pseudo-Boolean proof logging. So what we're going to do is, first, we'll steal shamelessly from the SAT community that has been doing this for over 10 years, very successfully, lots of different proof formats where DRAT is arguably the established standard. So we're going to steal as many useful ideas from DRAT as we can, but we're not going to operate with disjunctive clauses, but instead, just do this slight shift that our basic proof format is going to be 0-1 integer linear inequalities. And we're going to operate on these inequalities with what is known in the proof complexity literature as the cutting planes proof system. We're going to add to this proof system some so-called strengthening rules that I talk about later. And this has all been implemented in the VeriPB toolchain. And we're going to see in this workshop that there are a lot of different scenarios in which this just seems to work really, really well. So why am I giving this talk? Well, one reason, as always, it's a shameless marketing pitch, but also in the context of this workshop, I hope to tell you a little bit, give us a common understanding of the basics of the proof system, this cutting planes with strengthening that underlies VeriPB. I won't go into nitty-gritty details, but still try to get into some level of detail about what this proof system would look like. And then maybe also try to give a flavor of some of the applications that are possible. But of course, the purpose of the later talks is to do more about this. So somehow the whole goal of this first hour is I'll try to go as fast as I can to get through all of these slides covering this. That's my task. And your task is to slow me down with good questions to make sure that I don't get through my slides. Okay, this is like the adversarial two-player game that we have to play here. So I'll start with talking a little bit what we mean about proof logging and sort of the philosophy behind proof logging, what it would be. Then I'll talk about the proof system, and then some example applications, some possible future directions, some challenges that we have not been able to resolve so far. There will maybe be some such challenges also sprinkled throughout the talk. Okay. But I said it was going to be a marketing pitch, so let me start by the marketing pitch, because I think this is important to share this, to think about this, and this might be useful to you also. Where did we start? We started that with the desire to certify correctness of results, but it's important to realize, I think, that proof logging can give you much more. Firstly, we somehow said that, well, if we wanted formal verification, then that would be even better. I want to stress that in some sense, proof logging is a little bit orthogonal, because suppose you have a formally verified piece of software, state-of-the-art solver. You run it on a supercomputing cluster for a day. Then it's just a fact that one of these nodes somewhere will go down. Okay, and now you're not so helped by the fact that you had a formally verified algorithm, because what do you do if the hardware is bad? But the point is, with proof logging, if you run some kind of distributed process, at the end of the day, there will be a proof. And if there's a missing piece of the computation, there will be a missing piece of the proof. So you will actually have a certificate of the correctness of that execution, or you will see an error, or even if your algorithm was correct, but your compiler was wrong, or maybe even the supercomputer cluster was hit by cosmic ray, you can even detect that because the proof will be wrong. So in that sense, proof logging gives you very strong guarantees. I think some of the people who've been working more on implementing proof logging will guarantee that actually, if you start integrating proof logging early on in the process, it's an amazingly powerful debugging tool, because it allows you to run test cases without even knowing what the correct answers are to these test cases. And it helps you to find all kind of weird pathological corner cases that you're never able to trigger in the output. So the output of your 10,000 test cases look perfectly fine. Then you switch on proof logging, and the proof checker says, yeah, these answers might be correct, I don't know, but clearly you're cutting a corner in the proof here. And these errors tend to be like all over the place, although you're passing all your tests. But when you switch on proof logging, you can see that there are issues with the reasoning. Since proof logging tends to mirror what is going on inside the solver, proof logging provides sort of a new way of looking in depth into the execution. You can analyze the proof log and maybe mine it for insights to understand how the algorithm performed, how you can improve it further. And this is also like a new way of analyzing combinatorial algorithms. Sort of by definition, there are some buzzwords that are popular today. One of them is auditability. With proof logging, you have full auditability, because once you solve your problem, you just save the proof log. And if you know the proof format, then you can check this result many years later. Even if you don't have access to the original solver, you have the proof. Hopefully you have the proof checker. You can check that the result is still okay. And also, I don't think we've gotten there yet, but I just want to stress that in the context of artificial intelligence research, people are quite often interested in not only why are you reporting this answer, but what answer are you reporting, but why in particular did you find this answer? Okay, and when you have a proof of you're solving some optimization problem and you get that this is the answer, this is the optimal answer, your proof will tend to not only say that yes, this is the optimal answer, it will sort of inherently explain why, what constraints hindered you from getting an even better solution. And I think this is like in huge potential for future applications in the area of explainability. And I think we could do well if, when we're trying to talk to other people about proof logging, if we don't just try to sell correctness, but try to sell this whole palette of possible applications. Okay, so amazing proof logging. I hope you're completely sold now while you're here for the workshop, right? So, but let's now try to talk about what do proofs look like and how do we build the proofs. Well, the objects in our proofs will be 0, 1 integer linear inequalities. I'll think of them as just linear combinations of literals, so variables or negated variables. 0, 1 valued, where x plus the negation of x then is always cancelled and leave a 1. It's sometimes convenient. It's not really necessary, but it is convenient to use so kind normalized forms. I'll assume that all of the integers here, ai, and the so-called degree of falsity are non-negative numbers. I can always do this without loss of generality and efficiently, because if I have a negated coefficient here, I can just flip the sign of the literal instead. Okay? Most of the time, it won't really matter. On some slides, I will it will make my life easier if I assume normalized form. From the point of view of practical performance, you can have normalized form without loss of generality. Okay. And just to make sure we're on the same page, if you're more like a SAT solving person, you like your clause X or not Y or Z, note that this is in particular a pseudo-Boolean inequality. This is a 0-1 integer linear inequality. Just sum up the literals and say that at least one of them is 1. But importantly, and this is one reason why it's nicer to do pseudo-Boolean proof logging, you can write cardinality constraints efficiently, or like completely arbitrary constraints, like, I don't know, x1 plus 2 not x2 plus 3x3 plus 4 not x4 plus 5x5. Taking this weighted sum, it's apparently at least 7. Like, you can write completely general constraints like this. So this is our basic language. Like, every line in the proof basically is an object like this or manipulates objects like this. Okay, what do we want to do with this object? What is our wish list? Well, we can currently do with this, we can do like all of, I would argue, modern SAT solving, pseudo-Boolean solving, and optimization graph solving for decision problems, for optimization problems. There's active development going on, so it's like, it's a question whether it's presently available or real soon now or somewhere in between. Lots of work we'll hear about constraint programming, tree processing. There's work going on in automated planning, model enumeration, and we hope sometime in the future we'll also have multi-objective optimization, projected model counting, that we can maybe go to mixed integer linear programming. There's work by others on that, maybe all the way to satisfiability modulo theory solving. Although the red stuff is things that I don't expect to be fully captured within the format, the proof format I'm telling you about today. But I think that somehow, so one challenge will be to find nice and minimal extensions to what I'm telling you about now that would be captured, would capture all of this. But I'm sort of optimistic that the general ideas I will tell you about would be useful for all of these types of applications. Another thing that is important to when we're talking about proof logging, like how it's supposed to work, we're not suggesting throw away all the code you have so far, learn this complicated language, write new algorithms that understand this language, write a pseudo-Boolean solver operating with 0-1 integer linear inequalities. Like, this is very much not what we're saying. We're saying take your existing amazing solver, just add some print statements that will print 0-1 integer linear inequalities, potentially add a little bit of bookkeeping to make sure that you can print the right inequalities. Okay, so this is meant to work for like existing state-of-the-art solvers. Obviously, adding proof logging will take some time. What are we shooting for? Well, roughly, basically, the generation of proofs should be more or less for free. Think of it as, you know, maybe a 10% overhead in running time from generating proofs. Not saying that we're reaching it always now, but this is sort of, I would say that coming from the SAT solving community, this is maybe what you expect. Checking the proofs might be slower because at some point you have to sit down and carefully verify each step. So for instance, in the SAT competition, we have the order of a factor 10 more time for proof checking compared to actually solving. And you could say, well, why a factor 10? Why can't I check in the same time or maybe even faster? Like if you're a theoretical computer science person, you would like to maybe even have polylogarithmic time or something. We don't have that kind of very, very structured proofs because we're building the proofs on the fly. It would be wonderful if we could one day get down the proof checking time, but this is sort of, I think, what you should think about now. This kind of roughly the kind of performance that we would really want to have. And then a design choice, a design philosophy. We want to keep our proof language maximally simple. If we're going to do constraint programming, we're going to do Gauss elimination over GF2. We're going to do symmetry breaking. It sort of stands to reason that you could take your favorite tools or technique and you could add language for this. So maybe we start with cutting planes, then we add some notation for group theory and what groups are. We add some finite algebra so you can work in GF2. And then you could have like a beast of a proof system that understands all of this. This is very actively something that we chose not to do. We want to have proof logging for XOR reasoning, for constraint programming propagators. We want to have symmetry breaking, but we want a really, really stupid, simple proof format that has no clue of what a group is or what a CP propagator is. And one reason for this is that we're hoping to keep things really simple. I think we wouldn't have discovered the applicability of pseudo-Boolean proof logging over so many domains unless we had somehow, maybe it's a little bit by accident, but I think we've discovered that the basic reasoning works so well in many different paradigms because we forced ourselves to work, as it were, with one hand behind our back. And then one thing that you get from a nice simple proof system is that you can, in fact, then when you're getting to the proof checking phase, that is going to be easy enough that you can do it efficiently with a formally verified piece of code. So the gold standard would be when you're actually checking the proof, that is a fully formally verified process. You can really trust the result. Okay. Okay, so but how do we do this then? Well, if your problem is a 0-1 integer linear program or some subset, like it's a formally conjunctive normal form, you're in luck. I mean, your problem has the right format, so just add the appropriate print statement to your solver, and you're good to go. Okay. Otherwise, we somehow have to write your problem as a 0-1 integer linear program. Maybe the encoding is simple enough that you can kind of see that it is the right encoding. But again, ultimately, we probably want a fully formally verified translation. And then, importantly, it's important to understand that the solver won't care about this 0-1 integer linear programming representation. It will do its thing with the constraint programming instance or the graph or whatever. But when you write out the proof steps, they will be relative to your 0-1 ILP formalization. And it just seems that these 0-1 integer linear constraints are really hit the sweet spot between expressivity and simplicity. If you think about your favorite NP-complete problem, for instance, chances are you could write a really nice 0-1 integer linear program that encodes it. Okay. And the cutting planes proof system can perform powerful reasoning, but it's close enough to CNF and to SAT to be like really simple. Getting a little bit technical, I just want to highlight one more thing that is really neat when you move to linear inequalities compared to clauses. It will come up often that you have this. Here's our favorite constraint from before. Sometimes you will want to reify a variable, introduce a new variable R, and you want to say that R is equivalent to this constraint. So whenever this constraint is true, then R should be true, and vice versa. And you realize that this would be tons of clauses now, potentially. But I'm just going to flash this now and leave it as an exercise maybe. But if you just stare at these two 0-1 integer linear inequalities, they are actually encoding that R is taking exactly the same truth value as this 0-1 integer linear inequality. And this you can do like fully systematically. And with just two constraints, so it's like you can introduce new definitions in a very concise way. So then, okay, so what will in the end then be the workflow we had before? We had the solver getting an input, outputting a proof, plus an answer. Now our process, if your input format is not a 0-1 integer linear program, it will be slightly different. Your solver will read the problem and then say sort of, okay, this is the 0-1 ILP encoding I have in mind, and the proof will be relative to this. And the checker will check this, but then we'll have a formally verified checker that actually takes the original input and sort of checks that these two guys are in sync. And the checker, this is the VeriPB checker, will sort of simplify the proof a bit to make the formal verification process easier. So the formally verified checker will take the original problem in the original format and an elaborated proof and do a fully formally verified proof check process. So for many of the applications, again, if your problem is already in the right format, then you kind of sort of only need this box. But in several of the applications we will hear about, like subgraph solving, like constraint programming, ultimately you would want something like this whole thing with a two-stage process. Okay. So let me now tell you what what do the proofs look like? So this is sort of, this ends the, okay, so yeah, maybe this is a good point to stop and say, this is like ends my more philosophizing slides about proof logging. How do we do it? What are the goals? What are our design choices? And now we'll get down to, okay, what do we've also seen our proof language, namely 0-1 integer linear inequalities. Now we'll get down to how to manipulate them. Are there any questions at this stage? Yes.
You show on the picture before where CakePB.
So CakePB will be this guy, typically, and there will be like different. If you're doing graph problems, then there will be a graph version of CakePB that understands graphs. You know, if you do MaxSAT solving with hard and soft clauses, then there will be like a MaxSAT version of CakePB that can sort of parse this format. There, it's kind of easy because it's just an obfuscated. Really, it's an obfuscated 0-1 integer linear program, as Jeremias was telling us about yesterday. So sort of inside CakePB, you would expect there's sort of a deep down below, there's a pseudo-Boolean engine somewhere in here. And then another component is like this, making sure that these two translations sync up. And then sort of automatically you write your solver so that the solver and CakePB has the same opinion about how the problem is translated.
But when CakePB become the beast that understands everything, then
No,
no.
I have some of this in my slides.
Okay.
I'll show you how that works.
Somehow no, because it's so modular, right? So you're not like yeah, it's a good question, but somehow it's not really, because yeah, maybe it will be better to talk about it later. But basically, again, it's not a beast because it's just, for instance, okay. If you're solving max clique, CakePB, the formally verified checker, will need to do two things. Like, what will the 0-1 ILP encoding be? Well, you'll take the sum of all your vertices. Every vertex is a variable, and then you'll have a constraint saying for every non-edge you can take at most one of them. Okay. So one thing that CakePB will have to understand is that indeed there's a one-to-one mapping between solutions to the 0-1 integer linear program and actual cliques. And this is not a beast. This is sort of blindingly obvious. You say, do I even need to formally verify this? Well, you should, right? But it's kind of clear it's not going to be complicated. And once you have this correspondence, the rest is just going to be manipulating the constraints in this 0-1 integer linear program. So no beast inside. Make sense?
Yeah.
Any other questions? Okay. So what does a proof look like? Well, first there is like some kind of initial preamble that I won't talk about too much. Then comes what we think about as mostly the proof. We actually start deriving things. If it's an optimization problem, then you can also find and improve solutions. And then some things that are under active development, then there will be an output section where you could potentially list the constraints currently in your database. If you were doing problem reformulation as a separate standalone process, then maybe you rewrote your input to some kind of output, and the derivation section would then prove that these are kind of the same problem, whatever that means. Okay. And then there's a conclusion section where you can say, well, I got a CNF formula in or whatever, and it's unsatisfiable, or I got actually an optimization problem. Here's the optimal value, or at least here's the best upper and lower bound I can establish. Here is where we would also like to have other conclusions if you're doing maybe enumerating all solutions, or if you're counting the number of solutions, or doing Pareto frontiers of multi-criteria optimization or whatever. This is kind of work in progress. I won't talk too much about it currently. I would say satisfiability, unsatisfiability. So decision problems and optimization problems are well supported now. We have ideas for how to do some other things, but it's like in development. Okay, so we'll focus on the derivation section. In the derivation section, the proof will generate a bunch of constraints. Whenever from now on I say constraint, that's just a synonym for 0-1 integer linear inequality. And these come in two different flavors. There's the core set, which you can think of as your input formula. It might change a little bit later, but in some vague sense that I won't go into, it's always kind of equivalent to your input formula. And then there's everything else that you derive from these constraints. This could be something that your algorithm derives. Like, for instance, a SAT solver doing conflict analysis to learn new clauses, they will end up in the derived set. maybe the solver is doing some nifty symmetry breaking and just adding symmetry breaking constraints, then they end up in here. But you also need separate steps in the proof log to justify why these symmetry breaking constraints were okay. The solver are not aware of those, but we will generate them and put them in the proof log. Okay, so the derived set contains like both things that the solver learns and stuff that the proof logger will add to justify intermediate steps. Okay. And it's kind of clear that you have to be really careful with the core set because that's your input. Don't screw it up. I mean, then you've lost your input. The derived set is, we're not worrying so much because if you throw it away, you could always rederive it. I mean, we did it once already, so you could do it again. Okay. And then something that I'll mostly skim over. Well, sometimes there is an objective, which I'll also think of just as a linear function. And let me add a constant term so that without loss of duality, it's also normalized. So all the weights are positive. It's the trivial zero function for decision problems. During the proof, we know, like part of what the proof knows is the best bound seen so far. And then something that I'll mostly try to gloss over, proofs can also use a well-defined order relation. This is just a pseudo-Boolean formula, a collection of pseudo-Boolean constraints, 0, 1 integer inequalities, which encode a pre-order relation. And there's this, you have to provide then a syntactic proof that this is a pre-order relation. I'll mostly try to just gloss over this. Maybe we'll see something of this later in the talk about symmetry breaking. I'm not sure. Okay. So how do we do derivations? Well, we have firstly the constraints in the input formula. We refer to them as input axioms. Then at any point in time, I can just say, well, any literal x or not x is always non-negative. So that's like a literal axiom. And then what can I do? Any two inequalities that I have, I can add them up. Clearly, that's sound. I can multiply by a positive integer. That's sound. I can divide through by a positive integer. And now if it doesn't divide perfectly, then I can round up everywhere. You'd need like maybe 30 seconds of line to see that this is okay. It is okay. And then another rule that we also use is heavily that the constraint is written in normalized form. If the constraint is written in normalized form, and if I have some gigantic coefficients here, and this inequality holds, then without loss in reality, the same inequality holds where I've sort of truncated all coefficients here to be at most the degree of loss. Okay, this again requires an argument, but I'm just flashing this now, and we can talk about it later offline if you want to know it. This is sort of, 1 or 2 minutes offline, you'll convince yourself that this is okay. So these are like our rules for manipulating constraints. So let's see how you could do this. Suppose that this is an axiom, we can multiply it by 2. Here's another axiom in orange. Now we can add them up and get a new constraint. Then z, not z, is always non-negative. Let me multiply that by 2 and then add up these two constraints. And now for the first time, something interesting happens. Note that we have 2z bar, they cancel and leave a 2. Let me shift it over to the right. This sort of all happens between the scenes, right? So the summation of these two constraints is this constraint, where you always do cancellation and then shift constant to the right. And now we can divide by 3, and we're lucky because here we don't have any rounding on this side, but on the right-hand side, we get 2 1/3. And then what the rule says is that, well, this is all integral. So if it's strictly larger than 2, then you will agree with me that it's greater or equal to 3. This is what the division rule says. Okay. So lines in my proof will be something like this. And so I have to write it down in some way that the proof checker can understand. How will I do this? All constraints will have a number. Suppose this is constraint number 1. This is constraint number 2. When I want to refer to a literal being non-negative, I just write here tilde z, which means that, well, not z is, tilde is like another form for negation that we use in ASCII. And now if this is constraint number 1, this is constraint number 2, and this is the negated literal, then this derivation will look in the proof something like this. Okay, here comes a line in reverse Polish notation. Take constraint number 1, multiply it by 2. Take the second constraint, add up what you have so far. Take the literal axiom for not z, multiply it by 2, add up what you have so far, then divide by 3. So again, so what I expect to convince you about is that any derivation like this can actually be written as a line like this. So this is actually honestly like what proof lines will look like, except for the colors. Does this make sense? Okay, so we're doing some kind of syntactic manipulations. Now here for the theoreticians in the audience, no, one more slide, just to say so what are naming, we can have more expressive variable names. In fact, I was cheating a little bit. Variable names should contain at least 2 characters. They should start with a letter, but then you can throw in a little bit of everything. As I said, constraints will always be identified by a unique number, which is a positive integer. So I will talk about like constraint 42, and it will be clear what this constraint is. Whenever I derive a constraint, it gets the next available number. So like I have a current max counter. If I have 42 constraints in my database, and then I run this reverse Polish notation line, the result of this constraint will then automatically be constraint 43, because that's and then I just increase the count. Okay. And something that I won't go into, but the derivation rules, they come in 2 flavors. There's like a very strict restricted kernel format that is understood both by the nice flexible proof checker VeriPB in our case, and also by the more restrictive formally verified proof checker CakeDB. And then there's an augmented format that adds some things that make your life easier when you're using the proof system, but that's different forms of syntactic sugar, if you will, but that has to be removed if you want to talk to the formally verified checker. But I won't really go into this details. It won't be important for us. So, but for those of you who know what reverse unit propagation is, which is sort of a way of telling the proof checker that just do simple propagations of forced assignments, and you will see that what I say is true. That would be something that's available in the augmented format, but not in the kernel format. Okay, so for the theoreticians, you noted that compared to the cutting planes in the theory literature, we had not only division, but also this funky saturation rule. Do we really need both? Okay, it turns out that it seems so. Yes, in some cases, saturation is really convenient to have. Cutting planes with division is semantically complete, so you can always like simulate saturation by division, but the simulation might not be efficient. However, we don't know, like you can now define 2 different proof systems, like cutting planes with this rule or cutting planes with that rule, and we don't understand how they compare. Like we do know that there are some formulas where division it gives you exponentially more power over saturation. In the other direction, this is open. Just to point out that this is a somewhat intriguing open question. Okay, so those are, so far, everything we talked about is semantic, like I can derive new constraints that are implied. It turns out that sometimes I want to do more. I want to add constraints that are maybe not implied, but if suppose I have a decision problem, I can add C if I don't make the formula unsatisfiable. Like if F is satisfiable, then I should be able to add C if F union C is still satisfiable. When this is the case, I say that C is redundant. This is terrible terminology, but the stat people decided that this is what we're going to call things, so we just went with it, rolling with the blow. Okay, so here's without loss of duality, a constraint is redundant in this sense if the following holds, is redundant with respect to a set of constraints F, if F union the negation of C implies F and C under some restriction. Okay, this is always true. Okay, so defining C as redundant or defining by F and F union C being equisatisfiable or defining redundancy in this way is mathematically equivalent. Okay, this requires a proof, which I won't give to you, but let me just try to sort of hand wave the interesting direction. What are we worried about? We're worried about F being satisfiable by some alpha, but alpha violates C. So now we lost the solution. But then what this says that such an alpha satisfies F, it satisfies not C. So then alpha has to satisfy F and C under this restriction where I plug in the substitution omega. And if you just unpack what this means, it means that the composition of the substitution omega with the assignment alpha has to satisfy both F and C. Okay, and again, a substitution is just an assignment that can map variables not only to true or false, but it can also map it to other variables or limits. So this is like a general mathematical fact. If I would want to make this into a rule, the problem is I don't know how to verify implication. I mean, that's NP hard. So somehow I want an efficiently verifiable version of this. And one way you can do it is, well, do a bunch of subproofs, derive all of these constraints from this constraint. Okay? And if I do this, if I fire up a subproof where I derive each and every constraint over here, I also specify omega, then after this whole subproof ends, you should allow me to infer C. And something like this is what we'll have in the proof system. Yeah. Or sometimes something that I won't go into too much, but if the derivations are truly obvious, then sometimes we'll just dump this work on the proof checker and omit the proof, and then the proof checker will realize that, well, this was so obvious that I guess I should figure out the proof myself. And even the formally verified checker can figure out quite a few simple things by itself. And this is for efficiency reasons, not to avoid the proofs blowing up out of proportion. So let me just very quickly show how this can be done. Like we talked about reified constraints before. Suppose I want to define A to be true precisely when X and Y are both true. This is going to be these two constraints. This says, well, if A is true, then X and Y are both true. If A is false, then one of them are false. Okay. So, and if A is a fresh variable, I should be able to derive this. And the way I do it is, first I derive this constraint. What should my witness be? Well, I just set A to false, and then the witness doesn't touch F, so F clearly follows from F, and the witness just satisfies this constraint, so it vanishes. Okay. So now I've derived this constraint, and I want to do the other one. And then it's sort of, the witness I want to choose now is, why do I know that this is okay? Well, without loss in reality, I could always flip A to true. So this is what the witness will do. And again, I don't need to worry about my proof obligations for F because A is a new variable. And this new green constraint that I wanted to add is very happy because A was set to true. This constraint now, 2 not A plus X plus Y greater or equal 2, is not obviously happy because maybe it was using A, but I flipped A to false. But note now that I have the assumption that this constraint was false, and the only way this clause can be false is actually that X and Y are both true. So using this implies that this constraint has to be true because X and Y are both. And this is just, you can always, this is just an example, but you can always refine this way. And in fact, this proof is so simple that you just do this step and you basically tell the proof checker that figure out the details yourself. Okay. If you have an objective function f, then you also have to prove that, well, this patching omega will not make your objective worse. Remember that we're trying to minimize it. So the interesting thing is, once you write the proof in this way, it turns out that there are some things you can do. You can play with this and you can say, well, what if I have an amazing witness that is actually guaranteed to strictly improve my objective? But then it turns out that I can relax my obligations for what I need to prove over here. And I only need to prove that the original core constraint set holds under omega. So note that these are sort of incomparable. What happened, I'm asking for something stronger here, but now you can completely ignore the derived set. You can even ignore the constraint that you're trying to infer, and you only need to look at the course. Amazing. Okay. Why could this even be true? Yeah, so the witness should strictly decrease the objective, and if so, I get rid of all the cumbersome work of proving the derived set and the new constraint under omega. Sort of again, why is this true? Suppose for simplicity that there is no derived set, just to make my life a little bit easier. And suppose alpha satisfies C but falsifies the new constraint. Okay, but that means that alpha satisfies all the premises. So then I know that alpha composed with omega satisfies C, and it gave me a better objective function. Okay. So now there are two cases. Either this alpha composed with omega satisfies C, in which case we're happy, Otherwise, we're in a scenario where alpha composed with omega satisfies C and satisfies curly C and satisfies not C. So then I run the argument again, and I get alpha composed with omega, satisfying the core set and giving me a better objective. Okay, and now there are two cases. Either at this point we're satisfying the new constraint C, and then we're happy. Otherwise, I'm satisfying my core set, but violating the new constraint. So I run this again. And now I get alpha composed with omega, and it's giving me a better objective. But note that the objective function is like an integer, non-negative integer. So this just has to terminate. So this tells me that if this holds, then there would be some repeated sequence of omegas that would eventually give me a better solution. Could be an exponentially long sequence, but I don't have to do it. This is all in my head. I just need to prove this once, and then I can claim this new constraint in a one-shot derivation. Okay, and if I add the derived set, well, it works. I won't really go into details also because we started a bit later than intended and I have too many slides. Just to say one thing, that this is where the order comes in. Actually, in the fully general version, this sort of potential that you're working with doesn't necessarily have to be your objective. It could be any partial order. So here is like just to state the almost full formal details. The redundance rule would say that you can infer C if there's a witness that you have to specify that reproves the core set, the derived set, your new constraint under omega, guarantees that you don't make the objective worse, and respects the order so that at least you don't get anything larger. And then the dominant space says, oh, I'm actually strictly driving down the potential. I'm not screwing up my objective, and I am reproving the core. Okay, and syntactically it looks something like this. This will be such proof lines will not start with bold, they will start with red if you have a redundance rule, or dom if you have a dominance rule, and then you list your constraint. Then note that you have to specify this witness omega explicitly, and then you will have the list of subproofs if needed. Something that I just want to mention very briefly, you have to be careful with deletions now. And this is because of the dominance rule. It's kind of clear that if you delete too aggressively from the core set, then unsatisfiable formulas can turn satisfiable. What is not so obvious, you can even make satisfiable formulas unsatisfiable. Okay, this requires some thinking. But so you have to be really careful. And this is why we need to keep track of like what's the core set where we have our input and what's the derived set that we don't care about so much. The short version is if you want to delete anything from the derived set, that's fine, because we could derive it, you can always rederive it. From the core set, I can only erase a constraint if I prove to you that without loss of generality, I could recover it if I wish to. So I can only delete a constraint C from the core set if there's a rederivation of C from what is left using the redundance. This is getting a little bit technical, but sort of this is what the rule is. And in fact, this rule also we're kind of stealing from the SAT people, it turns out, but they never implemented it in their proof checker. But it's very important for us when we're doing optimization problems, and also when we're doing like fully verified pre-processing. It will be important to make sure that you don't introduce like spurious solutions that are too good to be true. In order for this to work, there has to be rules for saying, okay, I want to upgrade a derived constraint to a core constraint. You can do this, but not in the other direction. And then, in fact, if you want to get really fancy, like Bart, you might even change order halfway through the proof. Yeah, like you can do your dominance rule with respect to different orders, but whenever you change the order, you have to clear out the whole derived set, throw away the stuff you don't need. If you actually need it, you have to shift it to the core. And that means the next time you apply dominance, it's actually going to be among the proof obligations. So for decision problems now, yeah, I think I'm going to skip that. Let me just at a very high level say that what conclusions can you have now? Like in the concluding section, well, you can always say you ran for a while and then you timed out. You have no conclusions. You can say that you can have sort of a proof of satisfiability, which is saying that the formula is sat, and then you could potentially specify an assignment, or maybe it's already specified in the proof earlier. You had some kind of solution logging command. Or you can say that the formula is unsatisfiable. If you've explicitly derived contradiction, then tell me the number of the constraint that is contradiction. Otherwise, it should be obvious to the proof checker that the current state of the database is contradictory by just propagation. For optimization problems, you can find a new solution with the solution log and improve command, which will then add a constraint saying that, great, I found a solution of this value, now I want one better. And then you can use this objective improving or solution improving constraint to drive the search, to cut off parts of the search space where you know you cannot find better solutions. It's a little bit technical to say that this alpha should only satisfy your current database, which actually can be different from the input formula you started with. You can, in principle, run the proof backwards and recover a solution to the original formula from your proof. This would be interesting to do. It's probably somewhat non-trivial. We haven't done it. It would be great to do. And now we can see sort of what is a proof of optimality. Well, it's a contradiction derived from the request for a better solution. Like you found a solution, and now adding the constraint that I want something strictly better, this is contradictory. That's a proof of optimality. But it's important. This is another thing that people say, well, I don't care about proofs of optimality. Maybe you have an anytime solver. Maybe you just want to know how far off you are. Well, the proof system, in fact, supports this. In fact, this is what you prove. Either you have no conclusions, or you're saying, I found the following lower bound and the following upper bound. And the optimality proof would just be the special case when these bounds happen to match. Okay. For the lower bound, you can specify, you've actually derived that the objective is larger equal blah. This will be one constraint in your database, then you can state it. Otherwise, if you don't state it, the fact that the objective is larger than the lower bound should be obvious to your proof checker. Note that if you derived contradiction from an objective improving constraint, then everything is obvious to the proof checker at that point because contradiction has been derived. That's an important special case. And for the upper bound, you just give a solution, or maybe it has already been. You can stop at that point and give a solution, or you have used a solution logging and improving command already. And then the proof checker knows this because the proof checker keeps track of the best solution it has seen so far. Okay, so what can you do with this? Now, I don't want to go too much over time, so I'll just tell you that it turns out that one thing that is really painful in SAT solving, but is useful, is XOR reasoning. If you look at these clauses, from them, I want to say that, in fact, X and W take the same value. Why would that be true? Well, because it's just parity reasoning. We know that that is hard for standard conflict-driven closed-learning SAT solvers because there are theoretical lower bounds. Solvers do it anyway by sort of running Gaussian elimination on the side. This has been really hard to certify in DRAT. Now, if you want to do this, your first feeling is, I need a language for this. I need parity constraint, right? Like, how could 0-1 interlinear inequalities possibly capture parity? Like, it doesn't make sense. But it does. So here is the sneaky thing that we can do. We just introduce a new variable a, multiplied by 2, and then we derive that x plus y plus z plus 2 times a equals 3. And now I hope you agree with me that this says that the parity of x, y, and z is off. Because a, whatever it contributes, either it contributes a 2 or it contributes a 0, it contributes an even number. How will I do this? I will use the redundance rule if a is fresh. And I do the same for this other parity y plus z plus w. Again, it had to be odd because b is contributing something even. And note what happens now when I want to do, from these two parities, I want to argue that, well, then x and w, the parity of them are even. How can I see this? Well, just add up these, and now you see that from y, from z, and from A and from B, you're only getting even contributions, and you're getting an even number, so the contributions from here has to be even. Okay, and then it turns out that also the cutting planes proof system, thanks to division, it can very efficiently extract exactly this that you wanted, that indeed X and W are the same. Okay, and this is really, in contrast to previous solutions with DRAT, this is really efficient. It works blisteringly fast. It's really good. Another thing that Bart is going to talk about is symmetry breaking. Even if you're solving SAT solving problems, you don't have an objective. Well, I invented one. Namely what? I want to minimize the lexicographic order of my variable. Okay? And then I just break symmetries with respect to this. First, I derive with the dominance rule that, well, if I want to minimize and I have a solution and I have a symmetry sigma that would give me a lexicographically smaller solution, then that drives down my quote unquote objective. The dominance rule will do this, and then it's straightforward from this to get the standard symmetry breaking clauses, except this is what they look like in the proof log. Bart will talk more about this. Again, for the first time, you have fully general symmetry breaking for SAT solving, and in addition, it's efficient. Here are some questions. We don't know from a theory point of view whether you really need the dominance rule or whether redundant space strengthening should be enough. We do know that redundant space strengthening is enough to do like pigeonhole principal style symmetries, but this is a somewhat intriguing open question. Another very annoying question is that another way you can do symmetries is on the fly during search. If I've learned a clause and I know my formula is symmetric, I can learn a symmetric version of that clause. And that note that that's actually something that is semantic. It is implied, like if a clause C is implied from my formula, and the formula is symmetric with respect to sigma, then certainly the symmetric version is also implied. Yet this seems to be somewhat hard to do within our proof system. It can be done, like we know of a way of how to do it, but it's kind of cumbersome. And the problem is that these kind of extension rules, variable definitions, redundant space strengthening doesn't seem to mix well with the idea of like having substitution proofs or really proofs with lemmas, because what you want to do is like, well, you want to say if from the formula I derived a clause C, let me use that as a lemma and say, well, under symmetry, I have all of the premises. So then you should allow me to just apply the lemma and get the symmetric conclusion. This can be done. Again, I would be happy to talk about it, but it's like the current way of doing it, it takes several hours even to explain. So that's a bit painful. We can also do subgraph isomorphism. We don't really have time to talk about it. Hopefully we'll see more about it later. Just to flash one example, like what is subgraph isomorphism? I want to embed a pattern graph in a larger target graph so that I maintain all edges. Yeah, this is a graph problem, but then you stare at the 0-1 interlinear program for a while and you realize, what does this say? Well, every pattern vertex has to map somewhere in the target. That's this constraint. And then you say the mapping has to be 1-to-1. So for every target vertex U, it can take at most one pattern graph vertex. And then basically this constraint, if you look at it, says that, well, if B is a neighbor of A and A gets mapped to a target vertex U, then the neighbor B of A had better been mapped to a neighbor V of U. Okay, and if you think about this, you realize that this is like a fine encoding, perfectly kosher encoding of subgraph isomorphism as a 0-1 interlinear program. Like what is now totally not obvious, but what is true is that anything the Glasgow subgraph solver does to the graphs can be formalized as manipulating these linear inequalities. And you don't even need redundancy or strengthening or anything like that. You just need syntactic derivation. Okay, we're over time, so I won't do this example, except just to say, okay, so this is an example. For instance, if I'm doing my subgraph isomorphism, clearly A cannot map into U. Why? Well, because A has it has 3 neighbors and U only has 2, so I'll run out of neighbors. And it turns out that indeed you just have this small cutting planes derivation from this 0-1 ILP encoding, and when the dust settles, indeed you have derived that A cannot possibly map to U. And here the 0-1 representation, integer linear representation is important, and the division rule will be very important for this to work. So where are we going? What remains to do, except wrapping up this talk a few minutes late? Well, proof trimming would be great. We know for SAT solving that increases performance. It's also a way to analyze proofs, like to see what part of the proofs are really needed. It gets much more complicated for a proof format because you get all kind of weird dependencies when you're using redundance rules. Sometimes the proof files get really, really large. Again, the SAT people have a binary format. We should probably also have a binary format. You know, we should form a task force to come up with a binary format and a checker for it. Formally verified proof checkers, that's the gold standard, but this is already happening. And in fact, I see now I should update this with more references, because there are now 2 published papers with formally verified proof checking backends. As I mentioned, that you can go beyond just decision and optimization problems. You can enumerate solutions or models. You can count models. That would be great. Proof logging for mixed integer linear programming. In fact, there is an archive paper taking the VeriPB proof system and kind of porting it to a mixed integer linear programming setting. It's interesting. I don't know if anything has been implemented yet, but it looks like a very interesting paper. The satisfiability modulo theories people have been working a lot on proof logging in solvers like CVC5, Z3, and also SAT Interpol is missing from the list of. So again, SMT is Interpol. SMT Interpol is missing from the list of references. Sorry about this. I guess I ran out of space, maybe. But interestingly, SMT people take a very different approach. They have this proof system as a beast approach. Like they want proof language, syntax, and semantics for everything. So it's sort of, I'm not sure if that's the right philosophy, but that's, I think, is mostly what they're currently doing, except again, SMT Interpol might be slightly different. And yeah, using proof logs for analyzing algorithm performance, for explainability in artificial intelligence. I think there are lots of applications there. And many other problems and interesting ideas that I didn't have time to mention, although I'm already over time. So just as Bart already warned you that he will do at the end of his slide, you know, always at the end of my slides, you know, if this sounds interesting, and if you're thinking about the, you know, a postdoc position maybe in a little bit, or PhD position, we're sort of constantly hiring almost. So you should join the pseudo-Boolean proof logging revolution right after this workshop. There is, if you want to know some more of the details, there is a YouTube tutorial built on something that we did at CT 2022 with a video. Then there are updated slides for ICHKAI, further updates maybe for AAAI, though I'm not sure where they live. The best formal description right now is probably the SAT competition documentation for 2023. So there will be a new updated version. If you want to see how to use pseudo-Boolean proof logging for different techniques, there's a long and growing list of research papers. These slides will be online. I should have said that all of these references are at the end. There's like 10-something plus pages of references. And I think also if you go to the VeriPB repository, there are lots of small like proof logging files which you can mine for all kinds of interesting examples. Also, the VeriPB tool is kind of quite friendly. You can run it in trace mode and it will tell you exactly what it does. When it gets unhappy, it will tell you why it got unhappy. So it's, you can learn this proof logging thingy by doing to a large extent. So where are we? Why are we here? As I said, combinatorial optimization. It's amazing. NP hard problems being solved in linear time. That's not supposed to be possible. But here we are, except that solvers are seriously buggy. Like even the best commercial solvers are ridiculously buggy at times. We believe that the most principled, most promising way for addressing this is to have certifying solvers producing machine verifiable proofs. If you're buying this proof logging idea, And it just seems that cutting planes reasoning based on pseudo-Boolean constraints, 0, 1 integer linear inequalities, just somehow miraculously seems to hit the sweet spot between simplicity and expressivity. So yeah, the question is, what problems VeriPB can solve for you? Thanks. Any one or two very quick questions, and then we'll move on to the next talk.
There's something in the chat.
There's something in the chat. Aha. Let's see. Can I?
Yes, but
Yes?
I'm not sure if it fits into very quick questions. So
I think it seems we started already. So.
yeah, so I have a question about the redundancy criterion you had. So
Yes.
basically in the SAT context, there is a trade-off between so in the implementation, we usually try to have witnesses of length 1, but this only works if we have, if our alphas are total, basically. So I was wondering if there is a trade-off here too.
I mean, alpha only existed inside our heads, right? So the only thing that exists is omega. Let's see, here we have the full rules.
Yes, but if you want to translate a model back to your initial set of clauses, you actually have a concrete alpha.
Proof reconstruction?
Yes, if you do proof reconstruction, model reconstruction.
Model reconstruction. I don't know if we have any like, I think mostly when we use these rules, like what witness to use is somehow dictated mostly by the rule. If you're doing these new definitions or so-called reification steps, witnesses will just have size 1 and you will operate only on the new variable. If you're doing symmetry-based reasoning, then it stands to reason that somehow omega has to work on pretty much the variables involved in that symmetry. We do know, like, one trade-off we have is, but it's not really a trade-off for us. I mean, if you compare to SAT, the DRAT rule that I didn't really talk about, it's sort of the redundance-based strengthening rule, except that I force your witness to only operate on one variable. It has to fix that variable to a concrete value, right? That's
yes.
DRAT. And somehow, even if you're restricting yourself to domains of size 1, the possibility to be able to map that variable to some other variable or literal rather than just fixing it can be really helpful.
Okay, thank you.
Okay, so thanks again. Let's move on to the next talk.